Tra l'altro apparirà un bannerino. Apparirà un bannerino rispetto alle stringhe. Vabbè, questo non ci interessa. La registrazione. Sono finito da schermo. Registrazione corso. Divisione.
Guarda che almeno le specie per fare il cambio pagina. Se perde il focus, cominciano a fare a lavorare sulla finestra, perdono senti, non sarebbe il caso di fare la condivisione di tutto il desktop, così fanno quello che vogliono, perché sennò se cominciano a toccare questo.
Prova. No, prova 1, 2, 3. Ok. Sì. Mettiamo un attimo mute.
Pronto, pronto. Okay, good morning, all. Welcome to this fourth day of our conference and the first day of the third part of the conference, the first UMI meeting of PhD students. And so let me immediately give the word to Marco Cannassa, who is saying something about this new event.
This morning in this place, I should be there, but Barbara Nelli, who is the coordinator of the scientific committee of this event, this conference for young researcher, had a small health problem, so she couldn't make it. She sends her greetings, her wishes, and I join mine. We trust that these 2 days will be exciting for all of us, more than satisfactory for you, and we give you more interest in forming a community of young researchers in this country. We are also planning some form of publication, maybe through the journal of the Italian Mathematical Society. We will publications of papers originated from this conference and reserved for the participants in this part of the conference. So that's all. Have a good conference, and we'll be there for you. Thank you.
Guardo to Franco and Pazzo is saying something about a prize on legittimità of our department.
Good morning, everybody. I'm Franco Rampazzo, and I'm here to present you a prize that has been established around 2018. As everybody knows, that this department is named after Giulio Rigidita. Probably most of you know him, and some of you have participated, attended the theater piece that was given 2 days ago, Spaghetti and Rigidita. So the figure of this eminent, excellent Paduan mathematician is very well known. Let me just remind you that his name is attached, maybe the famous thing he has done is attached to this notion, important fundamental notion of parallelism, from which parallel transport, sorry, from which entire branches of geometry began. He, of course, is his name is attached to the theory of relativity without his and Richard's Bastros absolute hyperus. This theory would have not been possible to formulate correctly this theory, and then he did a lot of other things in his life, from studying three bodies problem to, or even very much applied things like for example, the wires under the ocean for the telegraph, important calculations. Mathematician with a very, very wide spectrum of interests. Okay, let me be short. There was, of course, you all know the sad part of the story. It was that in 1938, the Russian laws, he was expelled from all Italian institutions, Padova included. He was sort of emeritus in Padova. He was in Rome, but it has some recognition here, and that was cancelled in 1938. Okay, all over the world celebrated what this man was celebrated. Here we expelled him from all Italian institutions. So In 2016, it's not a reparation, unfortunately, but I mean, we tried to give the right light, its personage that it deserves, and we named this department after its name. Okay, after that, 1 year after that, we established this prize. We had already had one edition in 2019, which was extremely, I mean, I was in the commission and we are really enthusiastic. The level of young people in Italian mathematics is that level, we must be very proud. So now there is a new edition started last year, and the terms are still open. So this is an advertisement for whom, okay, there is a little bit of restriction in the subjects of this prize, which are mathematical physics, differential geometry, and variational problems. Okay, take these subjects, I mean, in the most wide meaning that we can have. And so please participate in this prize. So we will be very happy to judge the prize is, sorry, the prize is dedicated to the writers of a PhD thesis. That's so we have, oh, and sorry, last thing, I forgot to say that this is possible because very fortunate and generous support of Corvallis. It's an information technology firm that is spread all over Italy. And they, I mean, supported a prize in pure mathematics, which is actually a very good news, I mean, in the landscape, in the panorama of Italian mathematics, because I mean, it's sort of recognition of importance also of the theoretical part, even from the industrial and private sectors. So thank you very much. Sorry for yeah.
In bread of this it's about to describe and distributed on the ground floor. So let me just give a short announcement. Remember to keep the FFP2 mask. There will be no streaming of the lecture of today and tomorrow. Instead, there is the streaming from the lecture in this room, in the other room 1C 150 for those who cannot be here. As usual during this conference, we can send questions through the form that you find. I don't know if there is the slides of the address where to send questions. Okay, and please remember to keep the badge with you. The coffee break will be on the ground floor. And just a general orientation rule, there will be 10 sessions, so we have to see where to go. Remember that the first number corresponds to the number on the floor. So there is all the sessions on the first and second floor. So if it's 1C means the first floor, 2B means the second floor. Okay? So now I give the word to the chair of the speaker, and please.
My great pleasure to introduce the first speaker of the workshop and workshop this morning is Professor Alessandro Giuliani. He is professor at the University of Ferromagnet and he works in mathematical physics. In particular, he got very important results, statistical mechanics, and he got a prize from Accademia Nazionale dei Lincei, the Branch Prize. And he's also winner of 2 C projects, and he's editor-in-chief for Journal of Statistics and Physics, and his other editorial board of important journals like Communication in Mathematical Physics. So, he's the talk, he will talk about spontaneous breaking of continuous symmetry, right Heisenberg model, now we
Look here.
or the yeah, I will repeat it.
Thanks.
Sorry.
Yeah.
Okay.
Better to find the one stuff.
Okay, thank you very much for the introduction. Thanks for the invitation. It's really a pleasure to be here today and to have the occasion to well, open this part of the UMI workshop dedicated to the PhD students. So today I will review some aspects of the phenomenon of spontaneous symmetry breaking in statistical mechanics, in particular in the context of spin models such as the Heisenberg model. So the central theme, as just mentioned, is the notion of phase transition in statistical mechanics in connection with discrete and continuous spontaneous symmetry breaking. So I don't expect that you're all familiar with these concepts, and actually one of the goals of this talk will be to try to explain what these concepts are. So in statistical mechanics, the systems of interest have many degrees of freedom, typically infinite in the so-called thermodynamic limit. So we will be interested in spontaneous symmetry breaking in this infinite dimensional setting. But before going to that setting, let me illustrate with two very simple examples involving systems with 1 or 2 degrees of freedom, the concept of symmetry breaking. So here we have a system with 1 degree of freedom, say a particle moving in a potential well in 1 dimension, and in a potential well whose profile is symmetric under parity, under reflection x2 minus x. So if the potential is convex, so you have a unique global minimum, the particle, if there's some friction, will after a while sit in the only stable equilibrium of the system. So now imagine to deform the profile, so to keep the symmetry preserved, so this profile is still symmetric x minus x, but now the potential is deformed so that the 0 becomes an unstable equilibrium, a local maximum. So there are 2 global degenerate minima that are formed to the right and to the left. So if you do so, the particle will reach after a while one of the 2 global minima, either the right one, as in this picture, or the other one. So now you see that this is a system in which everything is symmetric under reflection, but the equilibrium reached by the system after a while corresponds to a configuration that is not symmetric under the natural symmetry of the system. So this is the phenomenon of symmetry breaking. It's a situation in which you have, in this context, 2 stable equilibria, neither of which is corresponds to a configuration that is invariant under parity. But of course, the set of the 2 configuration is invariant. One is mapped into the other under the symmetry. So this is an example in a system of 1 degree of freedom of discrete symmetry breaking. Here you have a discrete parity symmetry. Here you have the simplest possible system. This has 2 degrees of freedom, where you have an example of a continuous symmetry breaking phenomenon. So here the shape of the potential well is similar, but in 2 dimensions we have this set of infinitely many degenerate global minima, and after a while the particle will sit in one of these stable equilibria. There are infinitely many of those. None of them is invariant under rotation, but the set of the whole set is invariant. One is mapped into the other under rotations. Okay, so this is the general concept illustrated in a very simple situation. Okay, the situations we're interested in statistical mechanics, as mentioned, involve many degrees of freedom. So typically, the goal of statistical mechanics is given a microscopic model of interacting particle or interacting particles or interacting magnetic moments, say, give a procedure to predict the collective macroscopic behavior of the system. So one prototypical problem one can ask oneself is, given 1 mole of water that microscopically corresponds to a collection of about 6 times 10 to the 23 molecules of H2O, each pair of particles interact among each other with a well-known electrostatic force, which is the van der Waals force, which is known very precisely. So somehow at the microscopic level, you know everything. So how can we, from this, starting from this, understand, derive, compute the macroscopic behavior of the system? By macroscopic behavior, I mean, for instance, computing the equation of state. For instance, compute for any fixed t the equation for the isotherms. So this is a plot of the isotherms at high temperature or at low temperatures, and this flat region corresponds to a coexistence region between liquid and gas. Or how do I compute the phase diagram? So given 2 external control parameters, for instance, pressure and temperature, how do I predict that the system will be in a gaseous or liquid or solid phase? And say you are in the solid phase, how do I predict, starting from the microscopic equations, that the system will form an FCC or HCP or whatever crystalline lattice? So these are the problems one would like to address. Of course, I mean, it sounds complicated, and it is. But one good thing is that we have there is a well-established scheme, procedure somehow that, given a microscopic model for the system, allows, at least in principle, if one is good enough to compute limits of many variable functions, to compute thermodynamic functions. So this scheme is due to Boltzmann. It dates back to the second half of the 19th century. It has been, I mean, it's now extremely well accepted and accepted as one of the foundations of statistical mechanics. And roughly speaking, goes as follows. So, for instance, you want to describe this situation described here. So here you have a box I'm calling omega. You have n particles. Each of them, and the system of these particles is described by this Hamiltonian, where there is a kinetic energy term plus a pair potential, in which each pair interacts with the others with this van der Waals potential. So you're given this, and the Boltzmann proposal is compute the following limit, if you're good enough. So integrate over the allowed particle positions and momenta e to the minus beta h, appropriately normalized. Note in particular this n factorial that is related to the indistinguishability of the particles. Sum over all possible particle numbers with this weight, with this exponential weight. Take the log, divide by beta times the volume, and take the volume to infinity. Okay, this limit is guaranteed to exist if b decays to infinity sufficiently fast. It's enough that it's L1 at infinity. And so this limit exists, and it has the interpretation of pressure of the macroscopic system at inverse temperature beta and chemical potential mu. And there are other versions of this scheme for the pressure computed as a function of temperature and density instead of temperature and chemical potential. But so this is one version of the scheme. The density in this scheme is just the derivative with respect to this parameter mu of the pressure. Okay, so if you are able to compute this, from this you can compute so this provides the equation of state. In particular, you can derive the isotherms, say, and the location of and the phase diagram is constructed by identifying what are the coexistence lines here. And the coexistence lines are the values of in this language are the values of this parameter mu as functions of beta, at which the pressure is non-differentiable in mu. So this is the situation in which actually this equation is ill-defined. There is this pressure is a priori, so this limit exists, and the limit is a function that is convex in its argument. So this function is continuous, differentiable almost everywhere, and where it's not differentiable, it has a jump in the left between the left and right derivative. And this jump corresponds to the jump from the two possible values of density at a given choice of the external parameters. For instance, when you have coexistence between liquid and gas, you have coexistence between two phases that are which have higher and lower density. So phase transition in this language is characterized in terms of non-differentiability points of the pressure. Let me so one variant. So in view of what of this introduction, it's clear that one of the key interesting points in the story is to compute the phase diagram, in particular to identify these coexistence lines. So in a setting like this, can we prove actually existence of a phase transition from gas to liquid and to liquid to solid? And if we are able, can we prove in the solid phase that the system will form a crystalline solid with the same crystalline structure that we observe in water? Okay, I anticipate no, unfortunately, and this is one of the big open problems in the subject. Let me also start to connect this with the story of symmetry breaking I mentioned at the beginning. So note that some of this phase transition, not all of them, in particular the liquid to solid phase transition, comes together with the phenomenon of symmetry breaking, in this case of breaking of the translational symmetry. So we start with a system in which the microscopic model, the energy, is invariant under rigid translation of the whole system. But if the system will form a solid state at a certain point, the solid state will break translation invariance. I mean, a solid, once you realize it's solid, the location of the atoms in the lattice are specific and not invariant under all possible translation, but only invariant under some special discrete lattice translation. So this breaking from continuous translational symmetry to a discrete translational symmetry is one instance of this phenomenon of translational symmetry, of symmetry breaking in this specific context. So note that symmetry breaking does not come together with all possible transitions. So for instance, gas to liquid is not a natural symmetry breaking associated, at least not the natural one, while the liquid to solid has one. But okay, in many situations, the two things come together, even though there are caveats, as I just mentioned. Okay, actually from the formulation of the notion of phase transition in terms of the singularity of the pressure, it's not clear what's the connection with translational symmetry breaking. So there is actually another equivalent formulation in terms of infinite volume Gibbs measure. So the statistical mechanics of a system comes together with the probability weight that gives you the relative probability of any configuration, which is associated with this e to the minus beta h. So if you are in a finite box with finite number of particles, the notion of what e to the minus beta h means is very clear. When you take infinite volume, infinite number of particles, you have to be careful. So there is a notion, well-established notion of what is the good infinite volume analog of this e to the minus beta h. And these are infinite volume measures on an appropriate infinite probability space that satisfy this consistency equation. So the consistency equation, it's not important you read it in detail. It says that this measure here is an infinite volume Gibbs measure if its restrictions to finite volume in an appropriate sense are of the form e to the minus beta h. So this tells you that the consistency is that in any finite volume, the local weight is of the form e to the minus beta h in the presence of certain boundary conditions, and these boundary conditions have to be extracted with the same measure that you are trying to construct. So this is a self-consistency condition for this infinite volume measure that is called the DLR condition for the Brushin, for the Cruel. And the space of infinite volume measures at given beta and mu is non-empty, so there is at least one measure. It's convex. And it may consist of a single measure, but when it consists of more than one measure, this means that the system is in a values of the parameters, the values of parameters at that point correspond to a to the location of a phase transition, in which the different measure corresponds to different phases of the system. So, for instance, if you have two phases with corresponding to higher and lower density in a situation like the one I described before, these two infinite volume Gibbs measure correspond to the probability distributions corresponding to the dense, the liquid phase, and the less dense, the gaseous phase. Translational symmetry breaking in this context means that there exists an infinite volume Gibbs measure that is not invariant under the action of the group of symmetry that the microscopic Hamiltonian instead has. Okay, so this is one example. Let me move to the next example that will be more central to this talk, which is an example of a microscopic model for a ferromagnet. Here, ferromagnetic material is something like iron that at low enough temperature has the property that if you switch on a magnetic field, magnetic moments orient in a certain direction, so there is a global magnetization. Then you switch off the magnetic field and the system remains magnetized in the direction you induced with the previous presence of the magnetic field. So in a situation in which the system, the magnetization persists even when you switch off the magnetic field, you say that the system is in a ferromagnetic phase. Instead, in which when you switch off the magnetic field, the material turns back to be non-magnetized, you say that the system is in a paramagnetic phase. Okay, a simple class of models describing this situation is this one. These are lattice models, the lattice mimicking the location of the ions of iron, whatever. At each site, you have a vector here called S, and this vector represents the orientation of the local magnetic moment. And there is any configuration of magnetic moments comes with an energy that favors local alignment between these vectors. And depending on what the situation you want to describe, these vectors may be discrete. They can take either values plus minus one. This is called the Ising model. Or they can take values on a circle. This is the situation in which these vectors have two components. This is called the XY model or rotator model, or they can take values on a sphere. So this is the situation called so these are three component spin. The model is called the Heisenberg model in this case. Okay, notice that you can include an external magnetic field that favors alignment in certain prescribed direction. But if this magnetic field is switched off, the Hamiltonian, the energy is invariant under global rigid rotations of all the spins. So there is this at h equals 0 global invariance, that is the underlying symmetry I'm interested to whose breaking I'm interested to test. So in this context, the Boltzmann scheme reduces to computing the magnetic pressure, which is the log of the integral over all possible allowed configurations of spins of e to the minus beta h, divided by beta times the volume in the limit in which the volume tends to infinity. So this limit again exists, is convex in beta and h, and possible non-differentiability points with respect to h are a signature of a possible phase transition. So there is a general theorem, the Lee-Yang zeros theorem, that tells you that psi of beta h is real analytic for h different from 0. So no hope to find the phase transition at h equal different from 0, which is pretty natural. So when you force the system to take an orientation by switching an external field, you cannot have coexistence of different phases. On the other hand, at h equals 0, when you switch off the field, you may have situations in which you have coexistence between say a state magnetized in this direction or a state magnetized in the other direction, depending on the way, on the protocol you use to produce the H=0 field. For instance, you could have produced it by taking H to 0, starting from a situation in which the field was oriented this way or this way, and you produce possibly different limits. In a situation like that, the jump in the magnetization, the jump in the first derivative of psi at H=0 is a measure of this possible symmetry breaking of rotational symmetry. This value, it actually coincides also with the average of the height component of the spin at site 0, in a situation in which you first switched on a field in direction I and then you remove it. Okay, so proving that this m of beta is different from 0 is a way in this context to prove existence of rotational symmetry breaking. Okay, so in all these settings, there are very good, powerful methods to understand what happens when temperature is very large or density is very low. So this is the situation in the phase diagram of water in which you are down here. So, so you have very powerful methods, they work very well, but nothing interesting is happening there, no phase transition. So the big problem of statistical mechanics that was studied, is studied at least since 100 years, understand how to prove existence of phase transition and how to characterize them quantitatively. So the state of the art is very different depending on whether these phase transitions are associated with discrete or continuous symmetry breaking. Discrete symmetry breaking is to date very well understood. The basic building block is the so-called Peyer's argument. Is a proof that Peyer's proposed in 1936 to prove that in the Ising model with in 2 or more dimensions there is a phase transition at low enough temperature. This argument has been extremely influential. It has been generalized and extended to several other situations. It's at the core of many developments in the 20th century on the existence and characterization of phase transitions consistent with discrete symmetry breaking. In this argument, the key idea is that if you have discrete symmetry breaking, say 2 reference states, one magnetized up and one magnetized down in the context I'm describing, the low energy excitations are associated with the so-called Peyer's contour. So a contour separating a region in which the system is typically up, that is inside a larger region where the system is in a situation where the spins are typically down. So there are these bubbles of up inside a sea of minuses, and they are separated by contours, and the energy of these contours is what matters for the description of the system at low temperatures. At low temperature, these contours form a rarefied gas, which can be studied. So these contours are typically very small, very far away from each other, and they can be studied via perturbation theory very effectively. And okay, so this is good. Much worse is the situation in the case of continuous symmetry breaking. So from a heuristic point of view, the story was settled in the late 60s. So keywords here are the theory of the Boltzmann bosons, of the Higgs boson, spin wave theory. These are theories that emerged in the 40s, were developed further in the 50s, and well settled in the 60s. So in many respects, these theories tell you what should happen and give very precise predictions about the low temperature behavior of the system. However, strangely enough, only very few aspects of the theory have been substantiated with mathematical theorems. I mean, the rigorous understanding of this phenomenon, this phenomena is still very limited and partial. For instance, as I mentioned, there is no proof to date of the existence of crystalline solid phases. Good enough that there is a proof of existence of a phase transition for, say, the Heisenberg model or the rotational model, But even if there is a proof, there is no quantitative control of decay of correlations, and this is very unfortunate for comparison again with what happens in real materials. In the quantum setting, where one can pose similar questions, there is no proof of the existence of a phase transition for the quantum Heisenberg ferromagnet, and this is one of the most, I would say, embarrassing open problems in mathematical physics. Similarly, there is no proof to date of existence of Bose-Einstein condensation in systems of interacting bosons. And these are the two prototypical phenomena that are very well studied and still wide open from the mathematical perspective. Even though in both cases there are very precise predictions from, for instance, spin wave theory, telling you what is the low temperature series for the magnetization, what should be the exponent of characterizing large distance decay of correlations and so on. State of the art is in slightly better shape for models with abelian continuous symmetry rather than non-abelian. With abelian symmetry, you have little more methods to attack the problem. For instance, in the context of the n-vector models I mentioned, the case of an abelian continuous symmetry is the case of two-component spins. In that case, in the two-dimensional classical model, for instance, there is quite good control of the asymptotics of large distance correlations, and in three dimensions too. In 2 and 3 dimensions. And in the quantum setting, there is a proof due to Dyson, Lieb, and Simon on the existence of phase transition, but this proof does not generalize to the non-abelian case. In the rest of the talk, I will try to review the state of the art of classical and vector model in more detail than what I did so far. I will try to and state the recent results on the spontaneous magnetization for the 3-dimensional classical Heisenberg model. And then, time permitting, I will try to give some ideas of the proofs. I also prepared some slides on the quantum case, but I doubt I will get to discuss it. So let me go back to the classical and vector model. So I'm just rewriting the formula I wrote before. Now the only difference is that here, just for being definite, I'm choosing the direction of the external field to be the coordinate direction labeled n. So labeled 3 if we have a 3-component spin, etc. So this sum runs over nearest neighbor pairs in a portion of cubic lattice with periodic boundary conditions. J is a positive constant. These vectors, as I mentioned, are n-component vectors that have a unit norm. So for n equal 1-component spins means the Ising model, 2-component spins means the rotator model, and 3-component spins means the Heisenberg model. I already mentioned, but let me restate this here. The partition function is just the integral over the uniform measure over all possible spin configurations of e to the minus beta h. And infinite volume average with respect to this Gibbs weight is just this integral of f against e to the minus beta h divided by the normalization. The typical observables we're interested in are the nth component of the spin at side 0 or the scalar product between Sx and Sy. And we're interested in taking this weak limit. First, size of the box to infinity, then intensity of the magnetic field to 0. Again, this limit exists and is ergodic with respect to translations up to possibly extraction of subsequences. And ergodicity means in particular that if you take the average with respect to this infinite volume state with 0 external field of Sx dot Sy, and you take the two spins, the separation of the two spins very large, the average factors in the product of the two averages of Sx, Sy. This infinite volume state is translation invariant, so the average of Sx is the same as the average of S0. So this limit is the same as absolute value of the average of the spin at 0 squared, and this is also known to be the spontaneous magnetization. So what is known or expected for this m of beta and for the speed at which Sx.Sy tends to this limit? So this depends on many things. It depends on the dimensionality of the system, on the number of components, and on the value of beta. So let me start to review the simplest possible cases. So if you are in one dimension, any number of components, any temperature, it's well known that spontaneous magnetization is 0, and you have exponential decay of correlations. And you have a systematic way of computing the constants capital C and small c in this experiment. You actually have you can prove an equality with an asymptotic series with control on all terms. So this comes from transfer matrix methods and on the analysis based on Perron-Frobenius theorem of the transfer operator in one dimension. Okay, another very simple situation, 2 or more dimensions, any number of components, but inverse temperature very small, so very high temperature. In this case, again, m of beta equals 0, exponential decay of correlation, very detailed methods to compute actually the asymptotics of this. That is equal to a series in which you control in detail all the terms, and they are bounded, their sum is bounded this way. Okay, let me now move to non-trivial situation. So the first non-trivial situation, but as I mentioned, well settled since Pyers, is the case in which dimension is 2 or more, but the spin has only one component. This is the Ising model. The Ising model in 2 or more dimension at large values of beta has non-zero spontaneous magnetization thanks to this famous Pyers argument, which can be improved to actually produce a full series for m of beta. So one can compute a full series which is convergent in the parameter e to the minus beta, whose first terms are these ones, and you also prove that the speed at which Sx.Sy in average converges to this squared is exponential, and again you have a very detailed prediction about all possible things you want to compute. So here things are in very good shape. Okay, let me now move to continuous symmetry, 2 or more components. Let me start with 2 dimensions. So we have continuous symmetry, 2 dimensions. Notice that if the temperature is small, there is nothing to say. So the interesting part, the part of the story is temperature small. So in this case, there is a remarkable result known as Merlin-Wagner theorem that predicts, on the one hand, that the spontaneous magnetization is 0. On the other, that the speed at which the 2-point function decays is at least algebraic, with the prediction, explicit prediction on the exponent. So for any epsilon, the exponent is this one. So morally, it's -1 over 2 pi beta. Okay, natural question: is this upper bound sharp? This is expected to be sharp in the abelian case, rotator model. In this case, the best result to date, which dates back to 81, embarrassingly, it's this one due to Frederick Spencer. It's algebraic, but with a wrong exponent. This one is expected to be the correct one. Actually, it's expected to be the correct one up to exponentially small corrections in beta. So this is very far from the expected correct exponent. So here there is a natural open question. What is the correct key exponent? For 3 or more components, non-abelian symmetry, the conjecture is that the decay should be exponential, not algebraic. And this was predicted by Polyakov. His prediction came from an analysis of non-abelian Yang-Mills theories, which adapted to this context predicts this exponential decay at all temperature, which is called mass generation in the 2-dimensional Heisenberg model. This is a very big open problem. Essentially no results, but one result on the large N loop ON model by Dunilko-Penfeled, Samoti, and Spinka, who proved the exponential decay at all temperature. Yes?
in the notation, what is A in the beta?
Yeah, okay, there exists an A larger than there is a positive A such that this is true. But this is small, I don't know, it's 1/10, instead it should be 1. Not only should be 1, but the prefactor should be this 1/2 pi modulo exponentially small thing. So we are pretty far from the correct exponent here. Okay, let me move to higher dimension. So in higher dimension, 2 or more components, large enough beta. Here we have spontaneous magnetization. So we have symmetry breaking, breaking of rotational symmetry. Again, this involves Frederick and Spencer, also in collaboration with Simon. They proved in 1976 that this lower bound, their method of proof did not allow to obtain a full series for M of beta and did not allow to obtain information about decay of correlations. In principle, this additional information follow from a series of 8 works, 100 pages each by Balaban between 1995 and 1999, but it must be said that this series of papers, I mean, essentially nobody can understand it. I mean, there is no, presumably they're correct, but even the most experts cannot really follow the details. And so I believe they're correct, but it's clear that one would need a better way to derive this. So in a sense, the problem of computing the low temperature series of M of beta and of deriving asymptotic expressions for the correlations is open. I mean, the only results is hidden in a series of very hard to read papers. As far as the low temperature series for M of beta, there was in 82 a paper by Brickman, Fontaine, Leibowitz, Lipp, and Spencer who proposed a method that is much simpler. It is something like 10 pages paper, where they bootstrap the method of Frederick, Simon, Spencer to obtain a full expansion for the magnetization. But their method only worked in the abelian case. Also, they did not get sharp asymptotic bounds on correlation, but they got upper and lower bounds that for certain components match, are sharp from the point of view of the power law. In other case, for the longitudinal correlations, is not sharp. In the second line, the correct exponent is expected to be this one, and to date, there is no proof of an upper bound with the correct exponent. Okay. One recent result I would like to report, still unpublished, but I mean, we should be able to finish writing it soon, is a generalization of this result by Brickman and collaborators to the case of the Heisenberg model, to the non-abelian setting. So we have simple enough methods, 20 pages instead of 10, to obtain a full low temperature expansion of the magnetization for the Heisenberg model in, say, 3 dimensions, large enough beta. Here, these coefficients are explicit, so there is an algorithm to compute them. Unfortunately, our method does not come together with upper and lower bounds on the correlation. So the problem in the Heisenberg model in 3 dimensions of deriving matching upper and lower bound of correlations is even more open than for the rotator model. Okay, so the proof is based crucially as the proof of Brickman, Fontaine and company, and similarly to the proof of Frederick, Simon, Spencer, on a key method in this subject, which is reflection positivity. So I think I have 10 minutes more. So in the last 10 minutes, I would like to describe a little bit this method that is known to people working in this specific area, but typically not much beyond that, which is really central for this subject and for the understanding of this phenomenon. Okay, so reflection positivity is one of the very few methods available to rigorously understand continuous symmetry breaking. In a sense, it replaces the Peyer's argument which on the contrary is applicable in situation of discrete symmetry breaking. As I will comment more, contrary to the Pius argument is not very robust. It applies only to specific choices of the microscopic Hamiltonian, while the Pius method has the advantage of being very robust, and so they are allowing to understand discrete symmetry breaking in much wider generality than its continuous counterpart. Reflection positivity is a method that originates in constructive quantum field theory. Reflection positivity is one of the Osterwalder-Schrader axioms required for a Euclidean quantum field theory to be the imaginary time analytic continuation of a proper quantum field theory in Minkowski space-time. So doesn't matter that you follow the details of this dense sentence, but so the message is that it originated in the late 60s, early 70s as an attempt to provide rigorous constructions of relativistic quantum field theory using the approach of Euclidean path integral formulation. So in order to guarantee that the Euclidean theory is the continuation of a theory in Minkowski space with appropriate causality properties, one needs to require this reflection positivity axiom that for a while remained isolated in this pretty technical and specific area. Reflection positivity was later applied for the first time in the context of statistical mechanics by Frederick Simon Spencer in a seminal paper in 1976. This one that I already mentioned, where they proved that for the Heisenberg model in 3 or more dimensions, the spontaneous magnetization at low temperature is bounded from below by this quantity here. So I will try to sketch the method because it's surprisingly simple. It's very elegant, and actually it had many different applications beyond the specific constraints where it was originally introduced. So the reflection positivity is based on a smart trick. So you define the model on a cubic torus with periodicity. So a cubic portion of say ZD with periodic boundary condition of even side, and divide the box in 2 equal halves, say left and right. Now once you divide the box in two parts, left and right, there is a natural reflection connecting the right and the left. And any function supported on the left can be seen as the reflection of the function supported on the right, and vice versa. So if the Hamiltonian can be written, it can be decomposed in this form as sorry, here there is a plus. So it's restriction to the left half plus it's restriction to the right part, which is nothing but the reflection of the restriction to the left, plus an interaction left-right that is required to have this form. It's minus linear combination of terms of the form something times the reflection of the same something. So if your interaction has this form, and this is the case for the M-vector model, in which this interaction is nothing but the minus j sx sy across the line that separates the left and right half. Then correlation function of the form f theta f satisfy this positivity property. So here f is any function supported on the left. Okay, this seems some formal manipulation, but it's remarkable that this has many important applications. So the first one, pretty technical, is the so-called chessboard estimate. I write it down, it's not important you look at the details. It tells the following. So suppose that instead of having just one function on the left that you take together with reflection to the right, you have a collection of functions all over the place in your system. So you pave your system with tiles, and in each tile you have a function that is supported only in that tile. Now the average of this product can be bounded from above by a geometric average of other correlations, each of which involves a function that is obtained by taking just one of those representatives and reflected all over the place. So the point of this is that typically this correlation here is much easier to compute to evaluate than this, because this involves something that is essentially translational invariant. You start with something localized, you reflect it all over the places, and you obtain the observables that is essentially translational invariant. Actually, it's translational invariant. And this is typically pretty easy to, relatively easier than the left side. This chessboard estimate was used by Fröhlich, Simon, and Spencer to bound in a very smart way the following generating function of spin correlation. So they introduced this generating function of spin correlation by introducing this deformed partition function, in which instead of having sx dot sy, you have this square of sx minus sy. Minus this discrete gradient of external field. So here, if you take this at h equals 0 up to a global prefactor, you get the same partition function as before. But if you take a derivative with respect to h, this is a way to compute certain combination of spin correlations. Well, the magic thing is that if you now apply chessboard estimate, you reflect, and find out that after reflections, all these hx that are localized on one side are replaced for the purpose of the chessboard estimate to a configuration that is uniform, all equal to h0, say. So this tells you that this deformed partition function is bounded from above by the same thing at 0, which is just the standard partition function. And now you can use this. So this tells you that 0 is a maximum. So it tells you that the second derivative of this at 0, so the Hessian at 0 is negative. And this gives you, translated, this gives you an upper bound of certain correlations, spin-spin correlation. So this is sort of magic. This is called the infrared bound. It is now a very influential, I mean, this is a bound that has been proved in many different statistical mechanics systems, and it is at the core of the understanding of many systems with continuous symmetry. And this was, this paper of Fröhlich, Simon, Spencer was the first time where this was derived. And once you have this, you get a lower bound on the magnetization pretty easily, in which the same quantity appears as the deviation from the beta to infinity. Okay, I'm concluding more or less. So let me comment on good and bad features of this reflection positivity. So good thing is that when it works, it's very simple. So now I understand that you couldn't follow all the details, but the proof is really 3-4 pages long. And you need to use this positivity trick. It can be easily applied to systems with long-range interactions, like Coulomb system. And this is pretty remarkable because usually there are very few methods to treat Coulomb systems and to derive macroscopic electrostatics from a microscopic model of particles interacting with Coulomb. As I mentioned, it can be bootstrapped in combining it with Gaussian integration by parts to obtain higher order corrections beyond the first correction proved by Fröhlich, Simon, and Spencer. And it can be generalized to the quantum setting, where in the quantum setting, it is the only available method to prove continuous symmetry breaking, nothing else. This is a big problem. Bad features, it's very fragile against perturbations, contrary to the Pyers method. So the interaction in the Hamiltonian must be chosen in a very special way. In particular, it must be, in order to be reflection positive, it can only be either nearest neighbor or infinite range. If you take a finite range, it says that it cannot be reflection positive. It does not provide quantitative information on decay of correlations, and this is pretty bad. And it's very subtle to implement in the quantum setting, where it requires that in terms of the decomposition I showed before, This left to right interaction is realized in terms of matrices that are either real or purely imaginary. And this is a pretty unnatural condition for quantum Hamiltonians. In particular, it does not hold for the quantum Heisenberg ferromagnet. So it's very important to understand how to go beyond reflection positivity. The result, so either how to bootstrap and combine it with other methods, and somehow the result I reported on the low temperature expansion of the magnetization in the Heisenberg model was came out as an attempt to attack this problem here. In particular, would be very interesting to see whether it can be combined with more sophisticated multi-scale methods such as constructive renormalization. There are some alternative methods available for abelian continuous symmetry based on vortex representation, sine-Gordon transformation, and cluster expansion, which had a recent revival in the context of delocalization of discrete random surfaces and abelian lattice field theory. And some key names of contributors in this area are Rompeled, Christophe Garban, Chatterjee. But again, the non-abelian case is very difficult, and I see essentially no alternative to hard multi-scale methods. It could be such as those used by Balaban in the series of papers that unfortunately essentially nobody can understand. It may very well be that reflection positivity provides a priori estimates that could be combined with those methods to simplify things. And there are, I mean, I personally tried, many people tried in the years to combine effectively these things, but so far nobody succeeded. But I think that there is space to do better. And I think I will conclude that there was a part on quantum Heisenberg that I will just skip. Sorry. If anybody is interested, we can discuss on the side in the afternoon. I would be very happy. Let me move to the conclusions. Continuous symmetry breaking is a fundamental phenomenon in the theory of phase transition, but its understanding is only partial. I reviewed here the state of the art in the context of the n-vector model in dimension D, focusing on the classical case, skip the quantum. Spin wave theory provides detailed prediction of the magnetization and decay of correlation for different dimension and dimension of the space and of the spin. But substantiating with rigorous results this prediction is hard. Most of the non-results are based on reflection positivity, which is easy to apply, but too special. It would be very important to go beyond this method and to develop some. Here is a list of some open problems, some of which may be reachable in the next few years, some of which not. In the classical setting, two important open problems is in 3 dimensions, compute the asymptotic decay of transverse spin-spin correlations. Those in which the 2 upper and lower bounds derived by Brickman and company did not match. This should be doable, but it's certainly not trivial. Same for the decay in 2 dimensions. Can we derive a sharp exponent for the algebraic decay in the 2-dimensional XY model? And what about exponential decay in the case of non-abelian symmetry? Similar problem, harder problems in the quantum setting, the most important of which is to prove the existence of spontaneous magnetization in 3 dimensions for the quantum Heisenberg ferromagnet. There are very partial results on upper and lower bounds on the magnetic pressure. This is the part I skipped, but for the magnetization there are no bounds at all. It would be very important to make some progress there. Okay, sorry for being a bit late.
Question. I was fascinated by Jan Lepan talking about neural network works because you, by increasing the dimension, you render the space of equilibrium much larger and dynamic. It looks like there is some similarities in symmetry breaking. Do you know anything? Anyone made some kind of connection?
Well, typically models of neural networks, I mean, the starting point, very basic. I mean, there are more sophisticated models than that, but you have interacting spins with random interactions rather than ferromagnetic. So in that case, or if not random, at least they need to have oscillating signs, and maybe these oscillating signs are adjusted dynamically to answer, to react to some external impulse. So typically these are models in which interactions have not a definite sign. So reflection positivity, that, I mean, there are similar phenomena, but I mean, the reflection positivity doesn't work. There are methods to treat situations in which we have discrete spins, and in fact there are many rigorous results on spin glasses with Ising type spins, but as far as I know, results on disordered systems with continuous spins are not aware of results. Certainly these methods don't apply. There was
I mean, for some of the open problems like the sharp exponents, are there numerical indications of what the exponent should be? Or
Again, I mean, people, I mean, I also, but I mean, most people trust completely these heuristic theories that were developed in the 60s, 70s. I mean, there are so the predictions are amazingly precise, and any comparison. So numerical experiments are difficult, but any experiments that are difficult, but there are also sophisticated ways to compute critical exponents, and all the evidence is that for instance, in this that exponent 1 over 2 pi beta that I showed at a certain point should be the correct one up to exponential correction. So the correct exponent should be 1 over 2 pi beta plus order e to the minus beta. And this plus, there are even predictions on the prefactors in these exponentially small terms. So you know everything in principle, but proofs are not there. So there is recent results going in the direction of computing the correct exponent by Dario and Wu, who were, I think, postdocs of Rompeled. They studied not really the XY model, but they studied a simpler version of it called the Villain model. It's a model that it has also connection with certain models of discrete fluctuating surfaces. And for that simplified model, they computed the sharp exponent. But the application to the rotator model is still, I think it should be doable. I mean, this is one of those open problems that should be doable in the next few years. Others are more challenging.
The ferromagnetic case is at least historically the main example of historic behavior, where the actual value of the magnetization depends on the past history of the external magnetic fields and of the magnetization itself. Is it taken into account in your model, this factor? So when you have external magnetic field equal to 0, you may have several values.
Sure. This is exactly
on the past history.
Yeah, you mean the hysteresis cycle? Yes, this is exactly the fact that this is exactly the meaning of this non-differentiability of the magnetic pressure at 0. So there is a jump. So there is an interval of possible values of the magnetization at 0, which depends. So here is the history is not a dynamical history. So here the history is the way in which you produce the zero field state as the limit of a non-zero field state. So you start with non-zero field, you remove it, and you get a limiting state that, depending on the direction of the original magnetic field, will point in some directions. And you may even conceive other ways. Instead of magnetic field, you may conceive ways in which you have zero magnetic field, but you introduce boundary conditions properly designed that you then remove to infinity to produce values of the magnetization that are intermediate between the maximal and so essentially you have all possible values in a ball, and this depends on the protocol you use to construct the zero zero field.
Before to play the game, the speaker just remind that all the when I close will be finished. And we'll start the game at 10:30. So all the program will be morning shift of half an hour. Okay, thank you.